know if anybody's missing from the audience.
You mean you can run, but you can't
Puts the
hide.
pressure on us. Okay, so I'm delighted to be able to introduce Joachim ckler for the final talk of today. Gabor frames of totally positive functions, estimates of their frame bounds. Okay,
Thank you. Thank you for organizing and setting this meeting up. I'm really anxious to learn from the other two topics during the rest of the week. And I'm also very happy to be in Edinburgh. Very beautiful. Thank you very much. So I start talking or continue talking about Gabor frames today, and totally positive functions play a role in the second half of my talk. Going to Karl-Heinz and with Tobias Kloss, a Dortmund PhD student of mine, and with Jose Luis. Okay, so I have 4 sections in my talk. I want to explain the basic definition of Gabor families, the pre-Gramian matrix or Ronchen matrix, which was mentioned several times today. I also want to give a little bit of a feeling of the type of methods that I'm talking about today by this second section, which contains a proof for so-called painless frames. And it explains a little bit of the spirit of this talk, that much of the results we have obtained can be explained. They weren't proved in the beginning, but they can be explained in terms of matrix analysis. So in a sort of sense, in terms of numerical analysis of bi-infinite matrices. And then I go on explaining a little bit about rational lattice parameters, so which has a connection with Charlie's talk, and go into the totally positive functions, the longest section. So here's the definition of Gabor family and Gabor frame. Most of this you've seen today. We all use the same notation, except I use alpha beta for the lattice parameters. Some people used AB this morning, but the last talk used alpha beta as well. So there's a fixed positive number alpha beta. The product will always be less than or equal to 1 in order to make those results meaningful. But for now, a Gabor family is just composed of shifts by k alpha, modulations by L beta of a fixed function G. G is an L2 function, which I don't specify much further at this point. This is the frame condition. So all these elements, I'm sorry. The family of all these functions gives an equivalent norm in terms of the coefficients of f, or the inner products of f with respect to all these functions in my Gabor family. So here I have a discrete sequence, double indexed by k and l, and its little L2 norm should be equivalent to the cap L2 norm of f in L2. This is called a Gabor frame, and during the talk A and B, I hope, will always denote lower and upper frame bounds. I still detected a matrix denoted by A, which I corrected before the talk. So hopefully this was the only occurrence. There's an important result with Gabor families. Once you know your family is a Gabor frame, there always exists a dual family, which is also a Gabor frame with the same parameters alpha beta, which allows you to get this reconstruction or representation of f. So you take inner products with respect to one family and do the reconstruction with respect to the other family. And one of the issues in our work is also to find concrete or explicit forms for these dual windows gamma. We saw one specific dual window gamma, which was called the canonical dual during this talk, I think by Marcus, but I will talk about more general dual windows during my talk as well. So what are the problems that I'm interested in? We've seen this critical, or this set of lattice parameters alpha beta, which satisfy alpha beta less than 1 or equals to 1, which are drawn here. And one of the questions addressed in Charlie's talk was, what are families which generate this maximal set alpha beta less than 1, where you can choose parameters alpha and beta, which just satisfy this condition? What type of functions can you define such that all Gabor families are in fact Gabor frames? The white region is excluded by a necessary condition. It doesn't need to be considered further. So the maximal set, the necessary condition, was already published in the 90s, consists of these parameters alpha, beta, less than or equal to. This is for general G. The frame set is a subset of this dark region here, and frame set would be the set of all parameters alpha, beta, which generate a Gabor frame. There's another problem I want to address. Find explicit dual windows. I mentioned that. And the third problem is, if you know something is a Gabor frame, do you have any idea about rates or about bounds, lower bounds for the lower frame bound, upper bounds for the upper frame bound, in order to be able to talk about condition numbers of this decomposition? Now, the ratio of upper bound divided by the lower bound. In the previous talk, we have seen the Ronchen matrix. In the previous talks, we have seen the Ronchen matrix, which is again written down here. Given these parameters alpha, beta, and the function g, many properties, I wouldn't say all, but yeah, all properties of this Gabor family can be expressed in terms of this matrix. I give it an index G in order to distinguish between different windows. So the PG of X, D of X plus J alpha, and I put magenta in order to have kind of an association with row indices. And I put K beta in blue in order to have an association with column indices. So this is a bi-infinite matrix, and J rules over the rows, K rules over the columns, and G, this is a Gabor frame if and only if this matrix is bounded above. I wrote it down here. So it's a bounded operator with a bound independent of X, and it's bounded below. That's what people tell me in functional analysis. So closed operators are these bounded below. Adjective denotes there's a lower bound A greater than 0, which satisfies this condition. So this is a bi-infinite matrix acting on L2 sequences. I can restrict my analysis to an interval of periodicity, because you see changing X with a period of alpha doesn't change the matrix, just to renumber the rows, that's all. Much more can be taken from this Ronchen matrix. For example, you can find dual windows by constructing left inverses of PG of X. So if you find, let's say, a left inverse, which has the structure of a Ronchen matrix with a different window gamma, then you have found a dual window. The thing you need here is that, again, you have an upper bound for this operator defined by the matrix P gamma of X uniformly in X. So left inverses of the Ronchen matrix, in short, give you dual windows. And in many cases, you have a large selection of left inverses. So I will show you several dual windows on one of the slides very soon. Just to give a connection to what Charlie talked about is this can be considered as a sampling problem in a shift invariant space. You've got a shift invariant space, which I call V2G here. The 2 is here for the L2 norm. But there should be a beta probably down here because we're scaling, we are shifting by integer translates of 1 over, or integer multiples of 1 over beta. And its rows refer to the sampling points xj equals x plus j alpha. So this can be put in the terminology of sampling in shift invariant spaces. And this, in fact, was one viewpoint of the paper where we consider the Gaussian totally positive functions, which were mentioned in Charlie's talk as well. But this was only a side remark, so I don't go deeper into this terminology of sampling. Just in order to give you an impression of the methods I like to work with matrices of full rank. Then I know what a least squares problem is. I know how to solve it. I know how to write down the Moore-Penrose pseudo inverse. And I like to look at the Ron-Shen matrices in this form. So they are full rank matrices. They are by infinite, is the rank. But this condition on the lower bound here, this to me is like a full rank condition. The columns of PGX are linearly independent. Okay, so this is the full rank condition. So that's the way how I like to look at the Ron-Shen matrices in terms of numerical linear algebra, I could say. There's a result in these early papers by Dubuchy, Grossman, and Meyer, 1986, with a very simple proof where they show you have a Gabor frame of a window with a compact support. As soon as you know your beta parameter, so the modulation parameter, is less than the reciprocal length of the support. So with a support of 6 down here, take any function with a support of 6, anything in L2. You know immediately it's going to generate a Gabor frame if your beta parameter stays below 1 over 6. The proof is very, very simple by looking at the Ron-Shen matrix. They didn't. They gave another proof which is as simple. So I'm not providing simpler proofs. I just put it in the perspective of the Ron-Shen matrix. And the result is you see some entries of the Ron-Shen matrix column 0, right? So this is x plus j alpha. Column 0, k equals 0. So what's interesting, only the sum of squares of these values. Well, it should be a bounded function, I should have said. It can't be any L2 function. It should be bounded because this summation should be finite, and this summation should be finite, and well, I shouldn't have said any function. This condition should be satisfied. It shouldn't be too small. It shouldn't have periodic zeros or something like that in its support. So under these conditions, you get a Gabor frame, and the proof is very simple. You can write down the Ron-Shen matrix, and then you start thinking, well, when does this have full rank? And by the support property, here, let's say, is the 0th column. So I write down, I have a support length of R, and I write down the values of G of, I write down all the values, support length can be anything, and I write down all the values G of X plus alpha J, which are non-zero. So I'm in the support interval of G in my 0th column. Now I step 1 column to the right and change my arguments by 1 over beta. Well, if beta is less than the reciprocal of the support length, then 1 over beta is greater than the support length, so I step outside of the support. Of course. So I have zeros all the way to the left and right, and my Ron-Shen matrix has this trivial form. It doesn't need, there may be several zero rows, but then the next column will have another coincidence with the support. So these columns are all disjoint, I could say, and writing down the Moore-Penrose inverse is a trivial task. This is the Moore-Penrose inverse, the transpose of it. So you just take the same pattern, except you replace the AJs by AJ divided by the linear norm. So you have a wonderfully bounded L2 norm of this gamma, which is bounded by 1. So you have a canonical dual, consists of function values B1 to BR at the places x plus alpha j. So this is the form of the P gamma matrix that you're looking at. So this is the type of perspective I'm taking at Gabor frames today. So everything should be explained by the Ron-Shen matrix and its special properties. The painless result really comes down to this very, very small argument about a Moore-Penrose pseudo-inverse. What happens for a rational lattice? Rational lattice, I don't need rational lattice parameters, I just need alpha beta equals P over Q. You have a very simple relation explaining some periodicity in your Ron-Shen matrix, because x plus j alpha beta is the same as this, and every numerator here is, or this numerator here is 0 if jk of this form. K is a q times m, k is a p times m with m in z. So you see immediately that your Ron-Shen matrix is a bi-infinite block triplets matrix with diagonal blocks P0. Forget about this, which consists of gx plus j alpha minus k over beta, but j and k only run over some finite sets. So from 0 to q minus 1, from 0 to p minus 1. So you get a diagonal block starting at x in the upper left, and then going, well, q rows down, p columns to the right, with j and k only restricted to this finite set. You get q by p blocks, and then you go down in step by mq rows, and that brings you to the block P1, which has this fixed Q M alpha sitting in the row index, and then does the same with J alpha K beta J. So in this case, you get a block triplets matrix with finite Q by P blocks, and then you can use the technique of analyzing bounds for such a matrix, upper and lower bounds, using the standard triplets matrix theory. So you can view this as a Laurent operator. I use the symbol sigma g for this symbol that occurred also in Stork, I think. And then I hope I didn't miswrite things here. Except what you see is a dagger for a Moore-Penrose pseudo-inverse. So this is a Q by P matrix. For the upper bound, you take the usual S soup over both variables in order to get the upper bound of this Laurent operator before, and then you have to multiply with the beta in order to kind of connect with the Gabor frame properties. For the lower bound, you cannot take inverses, but you can take Moore-Penrose inverses. And as soon as this is uniformly finite, you're done. and you get the optimal lower frame bound A by this equation. So structured matrix allows you to turn things into a finite dimensional matrix valued. Omega is now a variable matrix valued problem, and then try to analyze properties of the symbol sigma g. If you write down these expressions, you would not see what's usually denoted by Cebulski-Sevy condition. In the case alpha beta is rational, but there is a way to convert these two conditions on the finiteness of both expressions into the Cebulski-Sevy condition, which uses Zec transforms of G, but I didn't put the formulation down, which you can find in Charlie's book on page 162. I will check. Well, he doesn't talk about Ronchen matrices. He talks about Gram matrices, which are the product of, or which are the representation of the frame operator. So they have the matrices PG star times PG. And if you take half of his formulation, I think 162. Anyway, so this was kind of the setting that I wanted to start with in order to get you kind of into the feeling of numerical linear algebra that we're trying to continue dealing with when going to other situations. Now, methods for Gabor frames of totally positive functions. And I want to let the parameters alpha and beta be more general than in the previous two sections. Here's again the definition of a totally positive function as taken from the work by Schoenberg, who connected them to Polya frequency functions, which I show on the next slide. So a real valued function is totally positive. You could say if the matrix set up in a similar way as a Ronchen matrix, where you have certain shifts yk and certain sampling points xj. Forgot to use magenta and blue here. You set up a matrix of this form, and this matrix, all these possible matrices should be totally positive. And total positivity is again explained here. All submatrices, well, yeah, all these matrices should have a non-negative determinant. So if you have a large selection of points and you cut out columns, you get smaller selections of points, and that's usually the total positivity of matrices, which requires that all minors are non-negative. But of course, this is included in this definition. Just cut out. Reduce n to a smaller number. Anyway, so this is a characterization of L1 functions in this class. Surprisingly simple, but still too difficult for us to cover all of them as we wish. Surprisingly simple. I think Charlie mentioned, well, there's a normally, there can be a positive constant, of course. Oh yeah, C should be greater than 0, otherwise it won't be positive anymore. But then you have a parameter gamma for the Gaussian, you have
Gamma non-negative, yes. Ah, yes.
oh, there it
Yes,
is.
yes.
Thank you. Gamma can be 0, so you don't have a Gaussian. And then you have these terms, which each by itself are, so to say, Fourier transforms of one-sided exponentials. E to the minus alpha nu restricted to 0 infinity, and then there's certain shifts in order to make this product converge in proper sense. So this is the form, and the condition on the alpha news mentioned by Charlie is written down here. So L2 convergence of the reciprocals. Okay. Our methods based on the Ronchen matrix allow us to deal with a special subclass, totally positive functions of finite type, where you have non-zero A news in here. Examples, maybe I just scroll down. Charlie presented this type as a convolution of the form e to the minus alpha nu x times a characteristic function of 0 is. Instead of writing this convolution, well, for some reason, I preferred this representation in order to show they're all linear combinations. I mean, this is a homework exercise for convolution. If you convolve e to the minus x and e to the minus 2x restricted to 0 infinity, you get a linear combination of both. Okay, so here we get linear combinations with a special property. The special property combines them in such a way that you get a Cn-2 function. So this is another way of those totally positive functions of finite type, where all A news have the same positive sign. So they all live on 0 infinity, and they are linear combinations of exponentials. That's all. Cn-2, so that this tells something how they behave at 0. It's boring to show a graph. Everybody can imagine this bell shape. Another way is divided differences can be thought of behind the scene. So this is a divided difference of the function e to the minus x dot evaluated at a1 to am restricted to 0 infinity. So there are several ways of putting these totally positive functions of finite type if they have all the same sign in their exponents. And then, of course, you have different signs, and then you spread over the whole line with exponentially decaying functions in the positive half and in the negative half with different exponents. You can convolve them, and this is written down here, and you can have polynomial factors in front. Those are the typical types we look at when we look at the positive function of finite type. Infinite type was mentioned by Charlie, like 1 over cosine 1 over hyperbolic cosine. The E functions do not appear here. Gaussian functions do. This was the first result that got us started at that time, which showed that this is a class of functions such that the frame set fills the whole region that is allowed for the parameter product alpha beta. Every alpha beta less than 1, you have Gabor. If and only if beta equals 1 happens if you have a type m equals 1. So that's why m equals 1 is excluded here because it will lie different. Anyway. Furthermore, in the same paper, based on the idea of left inverses of the Ronchen matrices, we said, well, there's a whole list of dual windows. We can vary this parameter L, and the next slide shows what happens if we vary it. We get dual windows of compact support. L divided by beta, so to say, determines how large we want to get with this compact support. And there's a distinction between these positive A news and negative A news, and. So the proof is very complicated, it extends over several pages, but it is a numerical linear algebra proof, in fact. Taking the Ronchen matrix, cutting a finite piece out of it, taking a pseudo inverse of that finite piece, and then showing we're done. So we take a row of that finite pseudo inverse, a finite dimensional pseudo inverse, and show this is enough in order to define the function gamma A. Maybe this was too fast. I will come to it a little bit later. Here's a typical graph of a totally positive function, very boring, and with exponential decay on both sides. And here's one dual we find. Well, not so nice, but here's a nicer dual we find. The x-axis has changed. So you see I've increased my L, my support length, and I get still a discontinuous window. That's still one disadvantage of our construction method. But as this L increases, the discontinuities somewhat get smaller. They don't disappear, but as L tends to infinity, we just conjectured without proving it, our gamma L windows will converge to the canonical dual, and the canonical dual has very nice smoothness properties. So, this was the work we did in 2011 or so. And I want to show a different proof, which I think is a little more accessible from point of view of numerical linear algebra. So this is my function G. I write down its Fourier transform, finite product of these reciprocals. And we have the 1 over a nu, doesn't matter which sign they have, for this type of proof in this formula. My normalization constant is G hat of 0 is 1. Anyway, so we fix alpha equals 1. All other cases can be done by scaling because the set of totally positive functions is scaling invariant. Once you know the result, that the frame set is full for one function, you know it for all its scaled versions. Because this is a kind of scaling invariant set. So the frame set is scaling invariant as well. So the pre-Gramian has this slightly simpler form. You have an x plus j, you still have the k over beta for the columns. This is a bi-infinite, totally positive matrix. By definition, every finite submatrix has a non-negative determinant. So all minors, all finite minors have a non-negative determinant. This is of the form x plus j minus k over beta as we require for totally positive. So now in the second proof, we found with the PhD student Tobias Close was in terms of some compactly supported basis. So we convert the totally positive function, which is this bell-shaped with exponential decay on both sides, so maybe only on one side if all the NUs have the same sign. We change it a little bit by a multiplication. Here's a finite product with these terms. What are those? Well, to numerical analysts, obviously, they represent factors. Well, just think of a nu equals 0 for a little while, and then later on they have to be non-zero again. But if this was an a nu equals 0, this is just a g minus a shift of g. So 1 minus the 1 shift of g, right? Now there's a little damping factor, or maybe if a nu is negative, there's a larging factor, which changes this difference. So there's another factor in front of the shift. So this is the real part, a nu, and this is the imaginary part responsible for the shift. And once you look at this formula, there has been a long history during the 80s concerned with exponential B-spline. In fact, Amos Ron, who was mentioned several times today, wrote his PhD thesis on it. I think it was in Tel Aviv with Niradin. So here's this PhD thesis on exponential B-splines, and if you look at it, I mean, standard formula for exponential B-splines. They have compact support. They have a nice convolution definition. So you take a truncated exponential function, but now here, we're only on 0, 1. So instead of a piecewise constant, you have a little bit of a, well, decline or increase, depending on the sign of A1. And then you take the convolution of these. And those of you who have seen the definition of ordinary polynomial B-splines are not surprised. So this works very similar to ordinary polynomial B-splines, where you convolve the characteristic function with itself n times. Here you convolve these cutout exponential functions n times, and then you end up with this exponential sign. There will be a picture, I think, later on. What does this identity up here tell us? Oh, should have said at this point, if you think about this in terms of spline theory, your totally positive function g would be the truncated power. And here you just do a divided difference, an ordinary difference. It's not even a divided difference. So when all these a nu's are 1, the corresponding g should be a truncated power, which is not allowed because it's not in L1. So it's not a Collier frequency function, but it is a totally positive function, by the way. So there we have another example, but it's not an L1 function. And then you end up with the ordinary B-spline. Anyway. So what is this transformation? What does this transformation mean for the Ronchen matrices? It's matrix multiplication of bi-infinite matrix PG by bi-infinite invertible bidiagonal triplets. Bidiagonal triplets. So you have a 1 on the diagonal, and you have an e to the minus alpha nu on the upper diagonal. That's all. Well, there's one thing I should say. If I talk about bi-infinite bidiagonal matrices, what's the diagonal of a bi-infinite triplets matrix? There was some theory about that. You have a choice. If alpha nu is greater than 1, then the small things sit upstairs, so you take the 1s as your diagonal. Alpha nu is negative, then the big guys are upstairs, so you choose this as a diagonal. This is the kind of numerical analysis back or thought in the background. This is by doing that, you make it invertible. By the choice of the right place for the diagonal, you make it an invertible matrix. Otherwise, if you would do the standard way, doing an upper triangular matrix and writing down its inverse with powers of the values in the upper diagonal, you would get a bounded operator. But now, since you have the choice of the diagonal, you can do it in both situations with alpha nu positive or negative. Choose the right diagonal. Once it is a lower bidiagonal matrix, if a nu is negative, and once it's an upper, if a nu is positive, then you put the 1s on the diagonal. So this is only a small remark here, but it justifies the word invertible. So now you have an invertible triplets matrix. You even know its norm, the norm of the inverse. You know its left inverse, etc. You know its inverse. You can write down its inverse. I'll do later again on another slide, but anyway. Oh. So now we're in this situation. We're not looking at PG anymore, but PNG. We have alpha equals 1. And we have n, we have a support from 0 to n, because we convolved n of those with a support 0, 1. So now each row, in each column, you have most n non-zeros. So this is the case n equals 3. In each column, you have only n non-zeros, because with further j's, you step out of the support, smaller j's, you're out of the support. Now you go one step to the right to the next column. Again, there will be only 3, and you will have jumped by at least 1. But then there are these nice situations where you not only when you step over to the right, when you not only gain 1 more 0, but 2 more zeros. So what does this mean? So here you just entered the support. Here you just entered the support. Then you're +1 within the support, +2 within the support, +3 you're out, because n is 3. Now you step to the right, +2 -1 over beta. Sorry, here you're in the support, +1 -1 over beta. 1 over beta is greater than alpha. So the x +1 -1 over beta, you're still outside and you only get back inside here. So these situations occur. You can even tell how often they occur. I call this a gap. So after going r steps to the right, you have gained at least one of those situations where you have had 1 0 once you step to the right. And the length is 1 over 1 minus alpha beta. So that's kind of a combinatorial argument. You gain by doing this plus j minus 1 over beta plus j, plus 1 minus 1 over beta, plus 1 minus 1 over beta, plus 1 minus 1 over beta. You gain like this 1 over 1 minus alpha is 1 in moment, 1 over 1 minus beta. Kind of gain as a you subtract from your x, and this pushes you out of the support. So very simple combinatorial argument that you see not only is your matrix banded, I call this slant banded, because you have this situation where you, well, a band which is continue here, but then you have the step go down and go down. So this, what I call slant banded, you have a slant banded matrix, and then you can try to do a little bit of numerical analysis of this banded matrix. So just to go back one slide, this situation where you convert your bi-infinite fully populated matrix to bi-infinite banded matrix works by multiplication with a finite number of bidiagonals. And this is one of the restrictions why we can do it for the infinite case, yet we cannot have an infinite number yet which does this. This replaces one of the steps in our original proof where we show something about linear dependence of certain sections of rows and columns of this matrix. You don't need to do that anymore, because now you have a banded matrix where 0 blocks occur, and you only need to worry about finding left inverses for this banded matrix. And to your advantage, you have the situation, if you follow the sign, it'll be on the next slide as well. Yeah. You have the advantage that within your matrix, oh, this is still black, this is red here. Within this matrix, you have portions which can be quadratic. Sometimes they are of size q by p, where q is greater than p, where nothing happens to the left and right. And this is obtained even if you have a larger bandwidth. For a larger bandwidth, you don't have kind of a diagonal block which can be inverted separately. But with these slant banded matrices, you always find these blocks. You have blocks within these slant matrices because at some places you jump down twice one to the right. You find these blocks where there's nothing to the left and nothing to the right. And then you're going to show that these blocks are invertible. Once you've shown that, which is just a citation from literature, you know that the full matrix is invertible, but you can because you can really decompose it into these diagonal blocks which can be inverted, each one piece by piece, or each by itself. So that's kind of the simplified proof, converting it to a banded matrix, showing that you have these gaps in the row indices when you look at the non-zero entries, and then pick out blocks where you can do discussion of invertibility. The discussion is only one sentence. Every finite block is almost strictly totally positive. Done. So now I know it's invertible, because what does almost strictly totally positive mean? It means that the determinants are all greater or equal 0, but they are actually strictly positive as soon as your diagonal entries are strictly positive. That is the notion coined by Gabor and Peña in 1995 of almost strict total positivity, which applies to B-spline matrices, exponential B-spline matrices. Of course, also found. Well, that's the list. I should there. Okay, so now you have such a block where you know the diagonal entries are positive. Nothing else happens to the left and right. Take the inverse of this block, get the assertion that you have an invertible matrix, and the get the constructive method for finding the dual window all in one. Okay. So I refer to the Gabor-Peña result. They started, or their work from 92 was one of the big papers, but it also continued till the late 90s, beginning of 2000. Gave many results that I will also talk about a little bit about the Turing's matrices. So left inverse is constructed by choosing this finite block of full column rank such that only zeros occur to the left and right, taking rows from the Moore-Penrose pseudo inverse because it's typically rectangular, will give you increase of the function values of your dual window. Here's the result we showed. For alpha equals 1, for example, alpha equals 1, we can show that all betas from 0 to 1 will belong to the frame set. So this, these lines should represent the conclusion from this result that all these points belong to the frame set. So for all parameters alpha, beta, which are marked either gray or black, you have a frame. And with this method, based on shift invariance in some sense, using alpha equals 1, 2, 3, so the spline space has integer knots. So that's why it only works for alpha equals 1, 2, 3. Otherwise, you lose the shift invariant structure of your spline space, etc. So in that sense, for the spline result, this is a rather special result. But since scaling invariance allows you to choose alpha equals 1 for the totally positive functions, this gives the general result for totally positive functions. Okay. I included the painless case here. Examples. I wrote lambda here instead of the A news. Well, but it's the same. So these are -2, -1, 1, 2. This is the corresponding exponential B-spline. And these are two dual windows that you can construct with this method. I suppose that I made a mistake in my include graphics command because these really look the same, but they shouldn't be. For a different type of exponential B-spline. Anyway, the explicit duals were constructed for very small parameters, beta even less than the support length should be 0 to m. Here, less than 1/2. This painless situation were constructed earlier. This is a doctoral thesis from Camilla Nielsen from Denmark. He was a doctoral student of the way. Anyway, so can we do a little more? And that's what I tried to do in the last very last part of my talk, can we do a little more concerning the frame bounds? So we've seen that bidiagonal matrices can be useful in this construction. They're not only useful, bidiagonal matrices characterize total positive matrices. Factorization of totally positive matrices, Gas-Capella, or going back to much earlier Cryer and 70s.
Whitney,
Oh, Whitney.
Whitney's paper.
Oh, sorry, I didn't go this far, sorry. So probably 50s then? Or,
Yeah, 52,
Okay.
51, 52.
Okay, so thanks for. Anyway, so they give a representation including the number of, where is it? The number of bidiagonal matrices you need, and this they claim is their own result. So they can write down an M by M matrix, an M by M totally positive matrix in terms of M-1 lower and M-1 upper bidiagonal matrices together with a diagonal matrix with positive entries. If the totally positive is non-singular. And then several representations which are unique with certain side conditions of something being 0 or non-zero, etc. So here's my notation for a bidiagonal matrix. It gets entries dj in the, here it is in the lower diagonal, delta j plus 1 thing. It's one diagonal. It's a lower triangular matrix. And you can write down every totally positive matrix as a product of M-1 such B news times a diagonal matrix times M-1 transposes of those B news with different parameters here. And in certain cases, you find those D nu J's by ordinary elimination procedure called Neville elimination, where instead of Gauss elimination for your given matrix P, you do some elimination technique using subsequent rows. So if you do the elimination from the left to get an upper triangular matrix, you don't do Gauss with your first row in order to eliminate the first column, but you start at the bottom, take the nth minus the n minus first column, get a 0 here. Then you take your n minus first and n minus second column, get a 0 here, walk your way up, come next. This is Neville elimination, explained very shortly. And the multipliers in Neville elimination are those D nu J's in some way. And then they rearrange those elimination steps in order to get only down to M-1 such bidiagonal matrices with non-negative entries. Everything has to be non-negative in order to be suitable for totally positive matrices. So maybe we can take advantage of this. But we have rectangular matrices, etc. So it's not as straightforward as I hoped. And that's why the result in the end is a little short. Anyway. So if P has bandwidth S, the number of factors is reduced from M-1 to S. You can go by bands. You don't need to do the Neville elimination. You can do it bandwise this way. This is all contained in the 95 paper by Gasca and Peña. And now with a simple relation of nilpotent matrices, everybody knows from linear algebra, you have its inverse right away. So these bidiagonal factors in M by M term have a simple inverse. You see the alternating and you see all you want to see for total positive or inverses of a totally positive bidiagonal matrix. You can see in here, and you get L2 norms or spectral norms of this inverse very easily once you know your Neville multipliers are less than 1. And that's the crucial part, which kind of makes me some headache so far. But anyway, so now how can we use it for our Ronchen matrix P and G? We have selected a finite portion, which is only zeros to the left and right, and we want to find upper bounds for its pseudo inverse. So P has full rank. P has this slanted band structure. It's a Q by P matrix, and it contains, well, P contains all non-zero entries of P and G in the corresponding groups. Find a factorization with these delta nu j's less than 1. If we can do this, then we have an immediate, here's an A left. Then we have an immediate estimate for, there are two mistakes. A should be P, and there should be a spectral norm, of course. I mean, this is the norm. This is the norm of P inverse. I don't know what's happened. Anyway, so this should be P inverse in the L2 norm is cap O of 1 minus alpha beta to the minus S with a simple argument. So very simple argument if you can do this. And well, what we could do is we could do it for the case S equals 1. So for a 1 where we only need a 1 bidiagonal factor, we could show that for the exponential B-spline of order 2, you can have a bidiagonal elimination matrix, which gives you a slant diagonal. I don't show the slant diagonal. I can do it this way. Okay, I could draw it on the board, but it gives you a slant diagonal matrix, which is positive, and the bidiagonal vector contains multipliers, which are all less than 1 minus beta. So you can get the result, the very simple result about the norm of the inverse in terms of the reciprocal of 1 minus beta. And taking reciprocal once more, you get a lower bound for the lower frame bound A in terms of 1 minus beta. Unfortunately, I could not extend the method yet. It is a little bit time consuming to B-splines of higher order, but I hope to be able to do this in some point and to be as close, produce these pictures where he shows the actual numerical computations of the lower frame bound, looking at the Ronchen matrix as a whole. If you cut out large portions, you get a good estimate for the actual optimal lower frame bound, and showing our analytic result for the lower frame bound, which is kind of by a constant apart, but it shows the same as asymptotic behavior as beta goes to 1. So you have a linear behavior as beta goes to 1, and that should be the end, almost the end of my talk. This linear behavior is known for Gaussian windows from much earlier work by Charlie, together with Yuri, Lubarsky, and Joachim. And in a very recent paper, Charlie told me that I looked at it. I think they find upper bounds for A, but no lower bounds for A, which are Lipschitz continuous. So it doesn't wipe our research out, but with much more complicated methods, of course. So kind of the theme of my talk was tell something about sort of simple methods from numerical linear algebra, which hopefully can help. And what I'm really looking for is input from people who know totally positive matrices much better, even the history much better than I do, and get some more techniques about finding inverses, pseudo inverses, or bounds on these factorizations. I mean, Gasca Peña, very nice papers, all existence. Nowhere you can find a bound. Thank you very much.
Do we have any questions?